So we left things with the applying validity to our calculator circuit. Right, so this lab is to apply validity to these four calculations. In my code, those calculations are here. So valid is the signal in my model that I'm using as my when condition. So I just apply that as a when condition and indent my code under that. Okay, so the lab was that simple. Compiling. And we can see now in the waveforms, drilling down into the FPGA, that we have gray now in the simulation. So these are all the diff-prod quote that I conditioned, and I can see now when they have meaning and when they don't. I can now ignore all the areas where they don't have any meaning. And what else? I guess there were questions about the generated. Yeah, the grayed out signals they're under a when condition that is deasserted. You will see values there. I mean, you do see numbers in gray. Again, Verilator is a two-state simulator, so we're not modeling don't cares in the simulation. They do have values. You can see the values, but you know that they shouldn't matter. Since we are using a two-state simulator and the current mechanism for checking of the when conditions is don't care propagation, we don't actually get that checking. So, in its current state, you can have errors where you're consuming things that are invalid that you shouldn't. But at least the theory of the feature is that you would get checking that would ensure that you indeed don't care about these values. You'll see in the diagram, now that we have applied the when condition to these four, you see the orange paths here, which I can highlight, connecting up valid, right? So the dotted connections are representing the application of this signal as a valid condition. And for those who are interested in the Verilog, we can open up the Verilog code. So I think we've looked at this view before. I can't remember. So this is showing our TL Verilog in the lower left corner. That goes through Sandpiper, and you have this sort of line-for-line Verilog file, and then this other Verilog file on top, which is generally correct by construction aspects of the code. So signal declarations, and in orange is logic related to the valid condition. So generally here the clock gating. So this is one of the clock signals that's conditioned on valid. I guess it's the only one. So the particular code that we gated was all just in one cycle. Does it even get staged? So this is the clock. Let's see where this is applied, actually. So the green is my flip-flops, and some of those flip-flops now are using the gated clock signal. So let's see what this one is. So this is the flop of our diff. Okay, so we do have a clock. We do have flip-flops now because we've gated these expressions, and these expressions produce values that do go through flip-flops. So each of these flip-flops will have a gated clock now. And it's all the same gated clock signal because it's the same pipe stage. So that's why we just have the one clock signal now. And we see that applied to, for example, this diff signal. And then this, I think, is this is the instantiation of the actual gator, right? So earlier we had the declaration of the signal. That's the output of this clock gating block, and this is the instantiation of the gating function itself. Okay. Any questions about this? Okay, so are you ready for the hardest lab of the week? All right, so often a calculator will have memory. So you'll have a little button that says remember the current value in the calculator, then you can do some calculation, and then there'll be a recall button. You push the recall button, and that value is loaded into your calculator again. So we're going to add that to our calculator. Just looking for my laser pointer. Okay. So we're going to add that memory. Okay, so that memory is state. All our state structures have this similar structure. They're a multiplexer with a recirculation path to hold on to the value, and then other paths for update, right? And they're going to need a reset state. So this 0 input here and the connection with, where's reset? Reset is giving us a reset to 0. So we're supporting two operations in this memory, the memory operation and the recall operation. We're going to encode, let's see, mem is going to be 5. Recall is going to be encoded as 4. So first we need an additional operation bit, because we're supporting more than 4 operations now. So we add a third bit to op. That's the first step, and that needs to be hooked up to the UIN bit that we were not using before. We need to add this mux. As I was saying, it needs to reset to 0. It needs to support mem and recall. So the mem operation needs to grab the value from out and load that into the memory. So that will be this path. Okay. So I'm choosing to loop that around on a 2-cycle loop because the operations are at least 2 cycles apart, right? So when I get a mem operation, the value from the calculation that happened 2 cycles ago is stable, right? I'm not going to change that the next cycle. So this could be a 1-cycle or a 2-cycle loop. It'll be stable in that window. So I've decided to implement it sort of consistently where every calculation is feeding the 2 cycles later, or 2 cycles later. So, so this path here is looping around the output to feed back into the memory for a mem operation. So if my opcode or my operation is 5, I'll select that path from the output 2 cycles ahead. 2 stages ahead, I should say. And if we're not valid, we'll do this retain loop. So I think that's everything for driving this mux. And then the recall operation is the opposite direction, right? If we have a recall operation, that's the 4 case here. We need to pull the value from the memory from 2 stages ahead, right? So this path coming out of the memory and looping back around to feed into the output, right? So if we recall, we grab the value from the previous calculation and feed it back in here. So that's memory and recall. We also, for this output mux, still need to have our recirculation path. We can, yeah. No, they're all going to both, right? So the muxes need to decode what the operation is to decide where to pull the input from, right? Um, these are two independent states, the memory and the output, right? I mean, this one's kind of drawn up in the corner, but they're analogous to each other. It would be easier to look at these lined up. That just gets in the way of the routing. But you know, analogously, they're both of them are doing an operation, and based on the operation, taking in the right updated value. Since the operation is 3 bits now, which can encode 8 values, we're only using 6 of the values. There's the possibility that our inputs are specifying an illegal operation. We'll treat those as no-ops, right? So in those cases, you want to just take the recirculation path just like you do for invalids. And what's the 4 here? This one? Yeah, so 4 is our encoding for recall. So this is associated with this line, right? If we're doing a recall, 5 is mem, right? So these paths are analogous but opposite directions. If you're doing a mem operation, you're going from the output into the memory. If you do a recall, you're going from the memory into the output. So if you're doing the recall, you're pulling the value out of the memory and loading it into the output. So this is the value, because of this ahead by 2, this is the value in the memory as updated by the operation 2 cycles ahead in the pipeline, right? Okay, I think I touched on everything. Any other confusion about this or questions? I'll let you work it through step by step. Yeah. Because we're adding 2 operations, the mem and recall are operations. So we have add, subtract, multiply, divide, mem, and recall. So we need to be able to encode all 6. Uh-huh. Green, where do I have a green wire? This one? Which? This one here? There's the green lines are the stage boundaries. It's connected up to this black line that we already have. So all the red here is the things that we're adding in. Should I talk this through one more time? Okay. I'll just talk it through one more time to be sure. So I'll do these in order, right? So we extend the operation to 3 bits to support the additional operations, which are encoded as 5 for mem operation, 4 for a recall. We need to add the memory mux. Okay, so it needs to reset to 0. When we turn on our calculator, it needs to have a predictable value. Capturing, okay, so it needs to capture the output on a memory operation. So that's this path. that loops around over 2 cycles. It needs to recirculate otherwise, so that's this path. And then we need to handle recall, which is sort of the opposite of that. So a value of 4 should select the input for the recall operation. So recall needs to take the value out of the memory and load it into the output. And we want to recirculate out by default if we have invalid operations. And, well, yeah, if we have encodings of the operation that are illegal, or if we have invalid cycles. Okay. So I think most people are there. If you're not there yet, don't worry. So I'm going to walk through the solution. Okay. So first we need to extend the opcode so we can encode mem and recall. So this needs to extend to 3 bits. And we need to use bit 6. Down here in my code, I still have these referring to just the lower 2 bits. So I should extend those now to 3 bits. Don't need the range anymore. But I need these to be 3-bit comparisons. So this is now an opcode of 0, 1, and 2. Now I'll add the memory mux. I'll do that right after the output mux since they're similar. So memory is going to also be a byte. It's also going to have a reset. I'm going to save the default recirculation case for last. It actually works better in the mux. So for the memory, the only case where I'm updating is when I have a memory operation. So if my operation is, and these should be 3 bits now, a 3-bit binary one, let's see, mem is 5, 101. And I also need to make sure that if I'm not valid, I'm recirculating. So I shouldn't be doing a memory update if I'm not valid. In my output mux, I had the not valid case after reset. That took care of all the not valids, and therefore these only apply if we are valid. I'm going to choose to structure this one the other way around, so I have to actually say valid and I'll be explicit about my parens here. We are a mem operation. Then the value that we want, okay, so we are here. Taking the value from the output mux, but with a 2-cycle delay. So I'm taking the value from the output mux from the operation that happened 2 cycles earlier in the pipeline. So that means a reference of ahead by 2. And this is from out. So my only remaining case is my recirculation. So let me just be consistent about my structure here. So this is my default. And my default case is to retain the value. Okay, so again, my memmux resets to 0. If I have a valid mem operation, I want to take the result of the previous operations, the result of the calculator as updated by the previous operation, which is 2 cycles ago or more. And otherwise, I just want to hold the value. By the way, there is kind of a shorthand notation, right? It's very common to have these state structures that are holding a value by default. We can also use this retain keyword that just means the value of the signal that's being assigned, but from a cycle ahead in the pipeline. So nothing we need to use, but so that's my memmux. And then the recall operation we have to support in the outmux. So let's go to our outmux and add a case. So now we need to explicitly check for divide. And have a default case. Not a default case. Have a recall case that gives us the value of the memory as updated by the previous operation. And then my default is going to be to recirculate the output. You could code this differently. These, not valid and default have the same behavior. In the case of this mux, I think it's easiest this way. And this is taking care of my default recirculation. So I think I hit everything. Yes. Sorry, which logic? The valid logic, you said? Equals in. It is from so it's all with everything is relative, right? So let's just do a waveform example. This is one stage after it's assigned. Yes. Right. We can move this expression to stage 0 and everything will be fine. Right. And that's sort of the nature of the magic here. We can move things around and no harm done. Somehow I lost the eraser. Anybody know?
Oh, it's faster.
Yeah. Oh, I thought this was a holder for it. So we have equals in coming in, right? So this is equal in, what is it, add 0? We could look at the stage 1 version of that, right? So this would be the @1 equal in, and then the valid calculation, that's okay. The valid calculation happens at 1 as well. This calculation is an expression based on equals 1. So it's checking that this guy is asserted and this guy is not. Right, so those are our waveforms. So if we move this expression and we look instead at 0 valid, this shifts over. And then, you know, we delay that to become @1 valid, which is used later, and it becomes this. Right, so we can retime the expressions and shift the waveforms around, but they're all doing the same calculation regardless. Other questions? Yeah. Right, so if we look at, and I'll just reach up here, I guess. If we look at what's happening, what's going through the pipe, right? If we have let's say we have an arithmetic operation, we have an add. Okay, so here's my add. That's in stage 1. We do the addition, we mux it, we capture it in the output. And then behind that, in stage 0, we have, what do you want to do, a recall or a mem? We'll do a mem, okay? So we have the arithmetic operation that updated the output. We have a mem operation that needs to capture that value, right? Clock comes along, these guys shift to the next stage. So again, this is my add operation, and this is my mem operation. We march along again. This is where I actually capture the mem operation, right? So the mem operation needs to capture in this mux the value as updated by this one, the arithmetic operation, right? So that's 2 cycles ahead of us in the pipeline. So we need to recirculate that one from 2 cycles ago, that output, back into this mux, right? Now I've drawn it a little bit differently. Maybe I'll think about reworking the diagram. I drew it through 1 mux and then coming around and going through another. Either way, it's 2 muxes, right? But really the expression of the logic that we need, it's pulling from this stage back into the mux.
If I am using the other reset is assigned to the reset is just like
Right.
0 set, but the second stage or first stage would be resetted after.
Right, and actually the cleaner way is to use the $reset. So when you're using the Verilog reset signal and expressions, and you move the expression around, you're changing the functionality of the circuit. If you create yourself a reset pipe signal and use that consistently, then reset gets applied to all the logic consistently. Okay, it's applied at different times depending on the stage. That's what we want. Okay, so we're essentially, when you create reset as a pipe signal, you associate it with the transactions that are going through the pipeline. So, no, that's what they told you. That's wrong. All right, you want things reset consistently. So we have this transaction that's distributed in time. What you want to be clean is you want to have some transactions be reset transactions, followed by transactions that are not reset transactions. Yeah, if you just slam reset everywhere all at once, you're resetting, you know, you've got random noise happening in the machine, and you apply reset everywhere. You have applied reset to parts of a transaction, but not other parts. And then that marches through and can be inconsistent. And if you take that approach, then you retime the expressions that involve reset, and now you're applying the reset differently, right? But if you're applying a dollar reset pipe signal, and you move the expressions around, the behavior is still consistent, it's still the same. I don't see any help with the scan for asynchronous. To me, asynchronous reset just causes mischief. It's not a question of synthesis, it's a question of methodology and how you code your logic. But so asynchronous reset, right? There's an asynchronous signal is going to propagate through the logic however it does and arrive where it arrives however it does. It's not necessarily arriving consistently. So when you distribute an asynchronous reset and then a clock comes along, some places see that reset, some places don't. And there's no guarantee that you're going to see it the same every time. So there isn't one reset flow. It can happen differently in different places, and there's no way to verify all those combinations. If you create a synchronous reset in one place and distribute that everywhere consistently, there's only one reset sequence. Yeah, same deal. When you power on, you have to, the power has to stabilize. After the power stabilized, you hold reset for some minimal number of cycles, you deassert reset. So again, you want to create that synchronous reset and use that synchronous reset everywhere. So if you have a 5-stage pipeline, just to repeat for the remote folks, if you have a 5-stage pipeline and you have a reset, the methodology that I'm recommending, you're going to use a dollar reset. It's going to take 5 cycles for that to march through the pipeline. That's fine. The reset, if I can call them reset transactions that we've created, those reset transactions are going to march through the pipeline, and as they do, they're going to clear their state as they go along, clear the state of the machine. You release reset, and now you have the opportunity to inject a valid operation in the front of the pipeline. So you've got these operations that are reset operations, and then here's your first valid one. The reset operations are marching through, clearing things out. The one behind it is marching along, doing something real. So reset's going to be held for a large number of cycles. The machine's going to stabilize. But if we just imagine that we're in some unknown state and we just have 3 cycles of reset, right? We have those 3 reset transactions going through. We don't have the machine cleared out yet. It's in some random state deeper in the pipeline, but we march along and we're cleaning up in front of ourselves so the valid transaction can come along. Yeah. So there's nothing special about 0. It just happens to be the number that has the first bit of logic in this pipeline. Yeah, everything in TL Verilog conceptually is part of a pipeline. TL Verilog does allow you to put expressions outside of pipeline scope like this. All that means is foo falls into a default pipeline in stage 0 of that pipeline. Meaning inside the pipeline or outside the pipeline? If it's connected up to other logic, right, if I needed to refer to it here and it's outside the pipeline, I would have to reach outside the pipeline to grab it. And reaching outside the pipeline, I actually have to give it an explicit, well, let's just stick with this, reference. So this would be, since I'm in stage 0, this is also assigned in stage 0. This would be a direct hookup to this foo. If I move it inside the pipeline, of course, I don't need this part. Any other questions? Okay, tea time. Okay, any lingering questions? All right, so shifting gears, so that's, we're done with our calculator, I think. I'm sure you've all heard a lot of buzz about RISC-V. Yeah, is there a question? You have an error? Okay, so I'll come back and look at it later. So I'm sure you've all heard a lot of buzz around RISC-V. There's a lot of drum beating. What's so novel and worthy of all the enthusiasm about RISC-V? It must be some revolutionary new CPU architecture, right? No, it's not. It's looks a lot like many instruction set architectures that have come before it. So first of all, it's not a CPU architecture. It's an instruction set architecture. It defines the instruction set. It defines the binary coding and encoding of the instructions and the mnemonic representation of those instructions. You know, as I said before, sort of the intermediary between the high-level language and the hardware execution. What is novel about RISC-V to an extent is that RISC-V is open. Okay, there has been a problem in the industry for a long time that instruction set architectures have patents associated with them. It's difficult to work with them in academia because of that patent protection. This isn't even a real issue. Many instruction set architectures are so old that all of the patents have expired. There's not really a real issue, but it's been such an issue traditionally that there's a lot of excitement about having that sort of openness from the start. What's maybe the most real aspect of RISC-V is that it's modular and extensible. So it's defined with these extensions. So you've got the base instruction set that's only, I don't know, 40 some odd instructions, very simple. We're going to implement almost all of them. So you can have very simple RISC-V cores that will execute programs. And then you have extensions that build on top of that. So the M extension for integer multiply and divide. You can execute code without integer multiply and divide. How do you do an integer multiply and divide if you don't have an instruction for it? You do it in software using other instructions. So if you need to do an integer multiply, but you don't have a native integer multiply instruction, you do some sort of a loop just like we did in grade school, learning long multiplication, right? That's going to perform that operation. So maybe since that instruction is, if you implement a RISC-V CPU without support for the M extensions, and the CPU encounters that instruction, it might take a trap to a trap handler that's going to do the software emulation of that instruction and then return execution to your code. So it'll function correctly. It won't perform those operations natively. It won't be performant for them, but it'll work. And so by layering on all these architectural extensions, you can implement cores with different characteristics that are appropriate in different circumstances. And also the RISC-V evolved with a community in place, right? So there was a community platform put in place around RISC-V and a process by which you can, working groups can form to define future extensions to the instruction set architecture, to resolve issues like what is the memory model for shared memory systems and things like that. So that's all evolved through the community, through working groups. And so it's that openness that's unique about RISC-V and the community-driven nature of it. Just to give you some pointers to various references. So kind of the hub for everything RISC-V is, didn't even write it there, riscv.org, I think. And I'll have to make that bigger to see the menu, apparently. So at riscv.org, it seems like every time I go here, the site looks different. It's an active community. But there's various information here. Probably the most meaningful places to look, the specifications are here. This menu looks different, so I'm not sure what I'm going to find, but somewhere under these are the architectural specifications, so ratified ISA specification. Yeah, again, this looks very different from last time I was here. Unprivileged ISA, okay, so this is what I was looking for. So this is the, I don't know, kind of the most fundamental specification for the RISC-V instruction set architecture. So that it's divided between the user space, which is the, well, say the privileged instructions, which are only accessible to, say, the operating system, the boot sequence, and then the unprivileged architecture or user architecture, which applications have access to. So this is what the applications have access to. And, you can read through this lengthy document in your leisure. Lengthy, but still much smaller than most architectural specs. Also, again, moved around on me. What do they call it? So I don't even see it anymore, but one of the fundamental things about this site, in my mind, is kind of the collection of resources related to RISC-V. So I kind of expected this to be front and center. In any case, buried here somewhere should be all kinds of resources related to RISC-V. So just a collection of all of the RISC-V cores that are out there. You can, if you create a RISC-V core, which you will do in this course, if you feel like it, you can come to riscv.org and find where they've moved the link to submit your contribution and provide a link to your GitHub repository with your core in it. give it a nice name, and it will be made available to the community here. You know, so architectural implementations of RISC-V, training resources for RISC-V, software, you know, ecosystem for RISC-V, so assemblers, compilers, what have you. So kind of the hub to collect all things RISC-V. Again, put in place by the RISC-V, you know, the creators and orchestrators of RISC-V, but driven also by the community. There's also, and I don't know if they've somewhere incorporated this into the site, but there's the RISC-V green card. Reference data green card. That's not this. I'll try the. Okay, I'm not sure which one of these links to follow, but let's see what we get. So this is kind of a one-page reference for the RISC-V instruction set, so it's a good, just handy reference. So these are all of the instructions that are part of, I don't know if this is RV32I, but these are the core instructions listed out in alphabetical order, it looks like. Okay, so here's the M extension. This is integer, multiply, and divide. The floating point extension, let me zoom in. Right, so these instructions are from the integer, multiply, and divide, M extension. This is the floating point extension, and the D extension is the double width floating point extension. And then you've got various reference tables, such as this one, which we're going to get into very soon, that help with the decoding of the instructions. And I think this back page here probably has a lot of other decode tables. So here we have kind of the register conventions, right? So I showed you the CPU is going to have a register file that contains 32 register values. Also listed here are these F registers. So the X registers are the integer registers. If you have the floating point extension, you also have these F registers, also 32 of them. So just looking at the integer registers, the X registers, all the X registers can be referred to as X number. They also have a name that reflects their conventional use. So conventional use meaning this is how compilers are intended to use these registers. You need those conventions so that when you're cross-linking code or you know, have different tools that are producing code that needs to work together, you need to have the same calling conventions for one you know, for one function to be able to call another and pass values to that called function. So for example, I think it's the A function argument registers that you can use to pass values to the called function. You have other registers. The X0 register is a special register. It's hard-coded to a value of 0. It cannot be written. Return address, so when you call a function, that function needs to be able to return to the caller. So when that call happens, you need to place the program counter of the caller into this RA register, return address, so that the called function knows where to return to. Some of these others we'll talk about as we go. What else is here? So floating point formats, we're not going to deal with floating point. Conventions for allocating memory. In addition to the instructions that are defined by the ISA, well, these are defined by the ISA as well, but the instructions that are natively supported by the machine, the instruction set architecture also defines these pseudo instructions that are implemented using other instructions, but they're so common it's convenient to have a mnemonic for them when you're writing assembly code. So, for example, this also illustrates the use of the 0 register. So, for example, there's no move instruction specifically to move a value from one register to another register. The instructions take 2 source registers and write to another. So move only needs 1 source register. So if you need to move, just do an add with 0 or an or with 0. So, you know, add a 0 to this other register and place the result here, that's a move. So because we have this 0 register that's always guaranteed to be 0, we can rely on that register to implement pseudo ops like move that are sort of degenerative forms of some of these other instructions. So you have a move pseudo op that you can use in the assembler, and that's going to assemble into, I don't know whether it's add or what, but something that is effectively a move. Okay. So RISC-V defines a bunch of different instruction formats. We've seen a few of the instructions in the microarchitecture and instruction set architecture. So there are some instructions that operate on 2 register values and produce a register value. Those are R-type instructions. There are some instructions that have an immediate value. They operate on a register and an immediate and produce a value in a register. That would be something like this. We have load instructions that load a value from memory. Those actually take on the same format as these. They have an immediate value, which in the case of a load is an offset value from a memory address. So the memory address is given in a register, and then you have an immediate offset from that. And that address is what you load to write the destination register. So the fields are the same, the format is the same. All of these have an immediate value, a source register, and a destination register. But syntactically, when you write these out in their mnemonic representation, you use a different syntax. Store type. So these have, this has, similar to mem, it's got a source register that's an address and an offset, but this other register is another source register. It's the data that you're going to store instead of the data you're going to load. We have branch type, which are going to take 2 source registers and an immediate in the form of a label. And U and J, we're not actually going to worry about too much. So let's see, U format has a larger immediate value and a destination. It's good for things like loading large values into a register, large immediate values. J type is for jumps. So jumps are basically in, the term jump and branch are used differently in different instruction set architectures. In RISC-V, a jump is an unconditional branch. So it just has, well, it has a destination register, which is used to capture the PC as a return address. And because it only has this one register, it's got a few additional bits available for immediate, so it can jump a further distance than the branch. So these are the formats for those types, right? So R type again has 2 source registers, source 2, source 1. Even though it doesn't look like it, these are both 5 bits and a destination register. The specific instruction is given by the opcode field and the funct3 field, and perhaps funct7. So these fields together narrow in on what's the actual instruction, right? Is it an add? Is it an or I? Sorry, R type wouldn't be or I. Is it an add? Is it an or whatever else? I type, instead of having the second source, has immediate bits. S type does not have a destination register, so we use that for immediate bits. So basically, each of these types, whatever fields are necessary, are used for that, and whatever fields are unnecessary become immediate bits. So B type does not have a destination register, so it's similar to S type, but the immediate bits are packed a little bit differently. U type only has a destination register and an immediate source value, and J type, again, similar to U type, but the immediate bits are packed differently. This table is how we're breaking down to the specific instruction. I guess I lied before. We break down to the instruction from the opcode and func3 for the most part. I think there's only one bit of the func7 field that sometimes is used to specify the specific instruction type. So this table uses the opcode func3 and sometimes this func7 bit or instruction bit 30 to define which instruction we're talking about. So let's look here at how to assemble a RISC-V instruction. So we'll take as an example this add I, x2 destination, x1 source, and an immediate value of 10. So assembling an instruction is the process of taking this form and turning it into bits. So we can start with this table. We have an add I instruction. Let's find add I. It's here. That tells us that we need these opcode bits and these func3 bits. We can also tell from this table that this is an I-type instruction. From there, so at this point we have our opcode, we have our func3, we know that we're I-type, so the format is this. And how do we get the rest of the fields? So since we know we're I-type, we look up the format of the of this string. It matches this format for I-type. So we just line that up with the instruction that we're given. X2 is RD. RD is X2. RS1, source 1 register, is X1. The immediate is 10. And we just put those values into those fields. So the RS1 field, the RD field, those are the register indices. So for register 2, we put a 2 into RD. X1, we put a 1 in here, and a value of 10 in the immediate bits. Okay, so that gives us all the fields of the instruction. Just looking overview of this, of course, this is the slide I'm working on when my wife walks by and looks at my presentation and says, "Oh my God, you can't show that to people." Throwing it all together on one slide, right, just so we can see the whole picture. You start with an instruction, and I've switched that up now to SLLI. We find it here. We find the bits that go into func3 opcode, in this case, this bit 30. We find that it's I-type. We look up in the format table and fill in RD, RS1, and immediate from RD, RS1, and immediate into here. Okay, so I'll give you a chance now to assemble an instruction. So try this instruction. Go through similar steps and see what value you come out with represented in hexadecimal for the 32 instruction bits. So you have cards, you have sheets. I don't have it up here. Sorry about that. I forgot to turn my mic on for the folks who are remote. Okay. So now the other direction, disassembling. So we're given a bit pattern. What's the mnemonic? Okay, so essentially the reverse process. We're going to do this with one table that we didn't use the other time to determine the instruction type. The instruction type can be determined from the opcode bits. The lower 2 bits of the opcode, the 1 we had before for the I extension, the base instruction set for RISC-V, these are always 1. So we use the other bits to determine the instruction type, and then we also factor in func3 and maybe this bit 30 to determine the instruction. So let's start with that. So we can use this table to determine the type from the opcode. Here, so we're looking at opcode bits 6 down to 2. So those are the bits that are circled here. So in this case, bits 6 and 5 are 0. Bits 4 down to 2 are 1, 0, 0. So that's here. So we're here in the table. So this is an I-type instruction. So now that we know our type, we know the format, so we know what the fields represent. So to 0 and 1 what? In the last one? Which 0? Oh, these 2 bits? Yeah, these don't factor into the type. Yeah, so what I just said, in the base instruction set that we're going to implement, these are always 1, 1. So to figure out the instruction mnemonic, we need to look also at func3 and maybe func30. So here we have func3 of 0 with an opcode 00100, and bit 30 is 0. So that matches up. That doesn't sound right. Is that right? That is right. That matches up with add I. So we know that we're an add I, and this says we're I-type, which matches up with what we found in this table. Okay. Basically, the types that I have listed here next to these tables are just a reflection of this table. So now we need to fill in the other fields, or examine the other fields rather. So we know our type, so we know what the fields represent. We know this is RD. That's here. So RD is 2. Destination register, we can fill in X2. RS1, those bits are here, value of 1, so we can fill in an X1. And these are the immediate bits. So our immediate bits up here are a value of 10, and we can fill in 10, decimal 10. Make sense? I mean, I-type is a little weird because it's got 2 different formats. This one's just for loads. We're not talking about a load instruction, so we're this format. Make sense? Your turn. Well, I guess just putting this all together first. So our process is to start from the instruction bits, which will be, well, instruction bits are laid out. We first take the opcode bits and look up in this table, find that we're I-type. So we know the format is this, and we can take the various fields and plug them into the format for I-type. And in this table, we can figure out which mnemonic we are from the opcode in func3 and instruction bit 30. Okay. So give this a try yourself. Here's the binary, or I'm giving it to you as hexadecimal. You can map that to binary and see if you can figure out what the instruction is. Q, X0, X1, BEQ, X2. So you're saying this is X2? This one's X1? So I think the syntax is that right? No, it's not right. Like that? We agree? So first we use our decode table, the opcode bits. First you translate the hexadecimal to binary so you can look at the individual bits. Lower bits are always 1, 1, and then it's going to be 0, 0, 0, 1, 1. So 0, 0, 0, 1, 1 puts us here. B-type. So we know we're looking for this format. Then we look at the func3, and I'm not going to do that, but that apparently matches up with BEQ. So those bits are apparently 0. So we know we're BEQ. And then we pull out the fields. So B-type, these are the fields. We pull out the RS2, which apparently is X2. RS1 apparently gives us a 1. And then this one's going to be source 1, source 2. They're always ordered source 1. It's always ordered destination register source 1, source 2. Anything that doesn't exist is not listed. And then the immediate bits all are 0. Professor Bopu was noting that there's no immediate 0 in the instruction encoding. You guys notice that? So the immediate is giving us an offset for the branch target. So it's pointing to an instruction. Instructions are 32 bits, so that's 4 bytes. So really the lower 2 bits of the immediate field should be 0. There is an architectural extension for compressed instructions, which can be 16 bits. So if you have support for compressed instructions, you might need, you might need an additional bit. But we don't need the low order bit that's byte granular. We need a 16-bit granular offset, right? So there's no point in wasting a bit in here that's always going to be 0. So the B-type encoding does not include immediate bit 0. That's just implied to be 0. Questions? All good? Okay. So let's play with paper. So pull out the instruction memory card. And again, this is intended to be front and back. So you've got the two one-sided memory cards, the one with the binary, the one with the encoded or mnemonic representation. So essentially, this will be timed. I'll give you 5 or 10 minutes to decode the instructions in your program. So have the instruction card showing the binary representation, right? You can hide the mnemonic representation. You should have these little R-type decode cards. If you don't have one, come up. This little card will help you line up the fields with the instruction bits. You have another card for I-type, so you should have cards for R-type and I-type. And basically, you can line up this card with the bits of the instruction to delineate the fields. So it's just an aid for the for breaking down the instruction into fields. So go ahead and do more disassembly of the test program. You know, start with the first instruction and work your way down. And we'll just see how far you get in 5 minutes. Okay, so however far you got is fine. It's just a little exercise to get comfortable with the process of decoding instructions. Next thing we're going to do is jump into Compiler Explorer. So I think we have maybe 20 minutes left today, something like that. So we'll probably finish up with writing a little program and playing with it in Compiler Explorer. So go ahead and open godbolt.org. Godbolt is the name of the guy who created Compiler Explorer. So we can do this exercise in any programming language, at least any compiled programming language. So C++, Java, whatever you like. And then we want to select RISC-V RV32i, well, RV32, I guess it's called, compiler. So RISC-V 32-bit GCC trunk is a good choice. So I will do this as well. Okay, so I've already selected this compiler. You can select it. The easiest way is to use this pop-out here and select RISC-V 32-bit. And then from this list, you can choose GCC trunk. You'll want to use these options, which I already should have. So I think I'm all set. I will make this big enough that it's readable. Okay, so godbolt.org, configure which language you want, configure RV32i, sorry, RV32, oh, I've got a different one in the picture, but configure RV32-bit GCC trunk, and configure your compiler options to these. I'll jump back there in a second in case you missed the compiler options. But once you get there, this lab is to write a program. You know, I think you're all comfortable enough with programming that this won't be an issue. If you're not comfortable with programming, not a big deal. You can ask ChatGPT to write the program. That's fine too. But the program that you'll write is a function called sum that takes an integer parameter called max and computes the sum of values from 1 to that max inclusive. So put this in a loop, each iteration of the loop, add the loop counter, and produce a sum. And then return the sum. As you write your code, the compilation is automatic. It's going to keep refreshing as you go. And so it should be the case, this will be our last exercise. We're going to use this program when we come back tomorrow. It should be the case that Compiler Explorer will store this in a cookie, and when you come back tomorrow, as long as you're using the same laptop, it should come up with that program. So I think we'll be fine. So that's the exercise. I'm just going to hop back here for 3 more seconds in case anybody missed these. Okay, so there is an option in here actually to execute your code, so you can test it. Where did I just find that? So under this output tab, you can check execute the code, I guess. And then this output box here, if you click on that, it looks like that brings up the, the output from compilation and execution. I'm not sure why I have an exit status of 0, but yeah, so it might be difficult to actually print because that needs a library, and I don't know how the libraries and everything are installed. I would probably just try returning, my exercise was just to write the function, but if you want to execute the code to test it, to write main if you're doing C or C++, and call the function and then return the result. Let's see what that does. I think that reran. Yeah, I'm not quite sure. It didn't seem to rerun this again. I haven't actually played with this before, the execution. So as you're playing around with this, you can play around with the compiler options as well. So you can change the optimization level and see how it affects your resulting code. You can, so you'll notice some fun things here. For example, if let's see if I can try this live. If you put this code into main, it doesn't work apparently. Let's hard code this as 10. Okay. Let's do it this way. You'll notice my program got rather small. Right, so what happened here? We were just looking at this over here, right? The compiler was smart enough to figure out that the whole result of your program is to produce a value that happens to be, I don't know why it's so big. What did I do wrong here? Oh, this is my factorial program, okay. So in my case, doing factorial, it actually computed the factorial. This apparently is 10 factorial, and it just returned it, right? It optimized my code pretty well. And you'll see at different optimizations levels, you might get different results, right? So here it's not doing the optimization because my optimization level is lower. So it's really fun to play around with these things and see the tricks the compiler does. I've seen it do some tricks that I would never have thought of myself. It actually does quite a good job sometimes. Okay, so as long as you have your program, you're all done. You can leave whenever you like.